And hello, AP Physics students. We have yet another example problem for you today. Today we are going to do problem number 50 from chapter number 6. Ooh, let's make sure that's on the screen. There we go. Okay, this problem states a 145-gram baseball is dropped out of a tree. All right, so let's draw our tree. And of course, we have our ground, right? And our coordinate system here. We'll use up as the positive direction, right? The plus y direction. And we have our baseball, all right? And that's falling towards the ground here, all right? What do we know? It says that the baseball has a mass of 145 grams. And being good physics students, we immediately just switch that over to kilograms since we know that's the unit that will work best in our formulas. We know that the initial height from which the baseball is dropped is 13 meters. We know the baseball ends up on the ground, right? So we're defining our coordinate system to be 0 where the ground is, and it says we're dropping the ball from rest. How fast will the ball be going when it hits the ground, right? Okay, so let's do our free body diagram here, right? Just one force acting on it, gravity. And what do we want to know? Well, in part A, the problem says if there is no air resistance, so if the work done by non-conservative forces is 0, right? How fast will it be going? Well, if this is true, we can say that the final mechanical energy of the baseball is equal to the initial mechanical energy of the baseball, right? In other words, when the ball gets down here, right? Okay, when the ball gets down here, it will have kinetic energy, but no potential energy. And to start, right, I have potential energy, gravitational potential energy. This is a Y here, but no kinetic energy, right? So the potential energy of the baseball up here, all 100% of it gets transferred into kinetic energy down here. Now, this is a very common equation, and if you solve for the speed here, you get v sub f is equal to the square root of 2gy. I'm not a big equation memorizer person, but this is kind of a handy equation to have in the back of your head, right? If there's no air resistance, you drop something from a height y. How fast is it going to go when it hits the ground? Well, square root of 2gy. And if we plug in all of our numbers here, 2 times 9.8 times 13, we get about 15.97, or with significant digits, we would get 16 meters per second. And that would be in the downward direction, right before it hits the ground. Okay? Okay, let's put a little box around that. Okay. Well, part B, there's a part B to this problem. And it says, what if there is air resistance, right? What if there is air resistance, and what if because of that air resistance, the final speed is only 8 meters per second? What would that force of air resistance be equal to? Okay, so let's go over here and amend our free body diagram here. We have a force of air resistance acting up on the ball. Okay, how big a force is that on average? All right. Well, here what we can say is the work done by non-conservative forces is not 0. Okay, that is the final mechanical energy will not be equal to the initial mechanical energy. Okay. Also, we can say that the work done by non-conservative forces would be equal to the force of air resistance times the distance over which that force acts. Okay? So we can kind of continue like we did over here. All right? But instead of the difference in these two being, oops, let's do that. Instead of the difference of these two being equal to 0, the difference is now equal to the work done by air resistance. Okay. Now notice that the work done is going to be negative. Why is this work done going to be negative? Well, the object's falling downward, the force of air resistance is upward. When that's the case, we have negative work being done. Okay, I'm going to plug in some numbers here. So we have negative force of air resistance times the distance we have fallen, all right, is equal to 1/2 the mass of the baseball times our final speed squared minus 0.145 times 9.8. Oops, running out of room here. Should have planned better, times 13. All right? Okay. So, doing a little bit of just calculating here. I get negative force of air resistance times 13 is equal to 4.64 minus 18.47. Notice only about 1/4 as much kinetic energy. My speed's only about half, but only about 1/4 as much kinetic energy. Interesting. Okay, negative force of air resistance times 13 is equal to negative 13.83 joules, right? Divide by 13 on each side, right? And I get the force of air resistance is equal to 1. Let's see, this is a negative and that's a negative, 1.06 newtons. Okay? Now notice that we're assuming here that this is an upward force. All right? It didn't ask for the direction, but just to be sure we could include that. All right? So the force of air resistance is 1.06 newtons upward, because if I multiply that force times the distance over which that acts, that equals the amount of non-conservative work done on the baseball, okay, or the change in mechanical energy. Okay, nice work, AP Physics students. We got a cartoon here for you as your reward. All right, we have an oldie but a goodie for you here, close to home. And how many Volkswagens will you think how many of you think the Volkswagen will clear the athletic field and eventually hit the old abandoned warehouse? Oh, look, we've got a physics professor talking some kinematics equations, right? And we got a Volkswagen, an old slug bug, and a giant cannon. And the caption says, "Thanks to the innovative labs of teacher Herb Crenley, physics quickly became Westvalley High's most popular course." Oh, wouldn't that be fun if we could launch Volkswagens in a giant cannon? How cool would that be? All right, nice work, physics students.